Well, hi everyone. I guess we all have to behave like fermions now. We'll get to that in the next lecture. In this lecture, lecture number 6, we will continue with the grand canonical ensemble that we introduced in the last lecture. And so today we'll first talk about the problem of adsorption as an example of the grand canonical ensemble. Then we'll move on to fluctuations in the grand canonical ensemble. And finally, a preview of the ideal gas. So let's talk about the problem of adsorption. It's a relatively simple application of the grand canonical ensemble. So let's suppose we have an ideal gas in contact with some surface, and this surface has M adsorption sites. A real example of this might be, for example, the surface of graphite and absorption of atoms onto graphite. So we have M adsorption sites, and it's a fixed number of sites. Now this is not the number of molecules, this is the number of adsorption sites on the surface. The gas and the surface are at a temperature T, and the gas has a chemical potential mu. And each absorption site may be occupied by 0, 1, or 2 gas molecules. The energy of a vacant site we'll call 0, so we'll reference all the energies from the energy of a vacant site. The energy with 1 adsorbed molecule will be epsilon, and the energy with 2 adsorbed molecules will be 3/2 epsilon. And we'll consider the case where epsilon is positive or negative. So we'll calculate the grand canonical partition function for fixed M adsorption sites, but where the occupancy, which we'll label as N sub I, at each site that can be 0, 1, or 2. So furthermore, we'll assume there's no interaction between molecules at different sites, different adsorption sites. So the grand canonical partition function, or grand sum, Z, will be Z1, which is the grand sum for one site, to the power M. That's the condition of no interaction between different sites. But the particles at each site do interact. How do we know this? Well, we know this by looking at the energies just above these energies here. Epsilon 0, epsilon, and 3/2 epsilon. Because the energy of absorbing 2 molecules at one site is not twice the energy of absorbing 1 molecule at each site, then we know there must be some interaction. So we have to use that more general form of the grand sum that we mentioned in last lecture. So we can see actually there's a little bit of attraction between the 2 particles here, otherwise this would be 2 epsilon. Well, the more general form of the grand sum, if you look back at last lecture, and we'll write this for the grand sum for one site, we sum over number of particles, and we sum over the energies of those n particles. This Gibbs factor, it's called sometimes, the exponential of minus beta epsilon minus mu n. Now, in general, remember that the values of epsilon here depend upon the value of n. But in this problem, there's only one energy value for each value of the site occupancy. So the grand sum in this case will be quite simple. And we just need to sum over n with appropriate energies. That is, there are only 3 possible configurations of one site. So the grand sum will have exactly 3 terms in it, 3 of these factors. So even though that the molecules interact, have an interaction on site, it's quite simple this way because, as I said, each configuration of n only has a particular energy. So that makes this a quite simple example. Now this is an important point, by the way, about the number of terms. So you ever get confused by this summation notation, Remember, whatever partition function you're using, the name of the game is to sum over all configurations. That's really what these sums are all about. So you have to understand what the notation means. And sometimes there are very smart ways to do this, by the way. But partition functions are summing over configurations. That's what they are. You have a term for every configuration. And for each term you have its energy. And if it involves grand sum, then you have this mu times the number of particles for that configuration. Okay? Hope that's clear. Well, in this case, it's pretty easy. We just have the three terms. Zero occupancy, no molecules occupying the site. 1 occupying the site, and 2. And you see the relevant exponential factors here with the energy and the chemical potential. So that's Z1. So now we'll use this grand canonical sum, or grand canonical partition function, to derive the mean number of adsorbed particles per site. We'll call that bracket N, and the mean internal energy, bracket U, as a function of temperature, chemical potential, and this energy scale epsilon. Okay? So let's derive the mean number of adsorbed particles per site, this bracket N, mean of N, and the mean internal energy, small u, small bracket u, per site as a function of the temperature, chemical potential, and epsilon. So, well, we can write that the mean N is just the sum over N times the probability of that. And we know what the probability has to be. It's just exponential factor divided by Z1. That is the partition function. And we can see right away that another way to express this is as the 1 over beta times the partial of log Z with respect to mu. Just operate on this, and you'll, on the partition function, or the log of the partition function, you'll see you get exactly this form. So that's a convenient way to express mean N. And so if we work this out, well, we can do either way. It doesn't really matter in this case. It's quite simple. We can actually work out an expression for the mean number of particles per site. And we have this expression. Of course, the first term gives us 0 because it's just a 1, and the probabilities, and we have these two terms, and we normalize by the Z1. And it looks like this. We can write it in beta. We can write it in terms of, well, here I have KT. This is Boltzmann's constant. Usually I write KB, but sometimes I get lazy and I just write K. That's what it is. Well, we can do the same thing for internal energy per site, U. It's just the sum over the probabilities times the energy of that configuration, like that. So we could in this example, it's very easy. We could just plug in the terms and calculate that. But just for fun, let's look at this derivative. Let's consider the negative of the partial derivative of log of Z1 with respect to beta. And so if we do that, we just take the derivative of Z1 here, well, Z1 was back here. You see what we get is this sum, and we bring down these terms in front of the exponential, right? And so we'll recognize that, of course, as the average internal energy minus mu times the mean N here. So we have this sort of relation here. And, well, let's just follow through and get that. Let's just explicitly, for this example, write out these terms. So once again, we have bracket u, little u, is this partial derivative. Well, we can see that this is, yeah. Well, let's just, what I'm saying is let's solve this for u. Let's write this, let's move the u over here and write this in terms of u, bracket u, and we get this expression. And now let's just work out this derivative from our partition function. And we'll see we get two terms here. oops, it looks like one of them got cut off. Well, you can see what this is. It's just this factor here. And we see that a number of these terms, a number of things in both terms cancel. So let's see. So this term, for example, mu times this factor cancels this one, and so forth. And what we're left with is, well, exactly what we would have had if we had plugged this in directly with the probabilities times the value of energy, right? So we could, of course, we could have found that directly, but what we wanted to show, what we were curious to see, is this relation here, and I just want to point out that that is true in general. And sometimes this gives us a nice way of calculating the internal energy. Okay, so for this problem, let's plot this mean N for a given chemical potential mu. And we'll consider both situations. We'll consider that mu can be positive or mu can be negative as a function of this energy scale, epsilon, for a number of temperatures. Well, we have a lot of parameters here, right? So there's a number of ways we could plot this because we have three independent variables, right? We have mu, we have epsilon, and we have temperature, or beta, if we want to express it in terms of 1 over kBT. So let's do it this way. Let's choose several values of this product beta mu. So we're going to basically scale the chemical potential by kBT, this energy scale of the temperature, right? So we use that as a scaled sort of inverse temperature, and we'll plot N versus, whoops, I lost an epsilon. We'll plot N versus epsilon over mu. I'll fix this. I left out something here which I can fix later. So what I'm saying is, here's a couple of plots. We're going to plot on this side. We're going to plot the mean N as a function of epsilon over mu. So we're going to use scaled variables, right? So we're going to plot this as epsilon over mu, so it makes it dimensionless. And we're going to do this for several values of beta mu, which is a scaled inverse temperature. So basically, beta mu really, really large, going to infinity would be 0 temperature, this blue line. And then as we raise the temperature, we can plot this for different values of beta mu. Here's 10, and the yellow is 2. And here is epsilon, and we're just scaling epsilon by mu, so it gives us a nice plot. I mean, you know, if you really wanted to this, you could say, okay, I'm just going to let mu equal 1, and then I'll plot everything in terms of mu. That's kind of what we're doing. And so what you can see is the occupancy, that is mean N, we can call that the occupancy of a site, has this step function that really, as we go to t equals 0, to 0 temperature. There are two particles sitting at this absorption site at really low energy, and as we raise the energy and we get to a certain point, you could actually work out what that is. Then at low temperatures, the occupancy goes from 2 molecules to 0 very sharply in a sort of step function. And as we raise the temperature, this gets broadened out. And this is the case for positive mu. Well, it's interesting to look at the case of negative mu, which is over here. So once again, we're going to plot different values of beta mu. Here, well, since mu is negative, I'm essentially taking the absolute value, but I'll write minus beta mu here. Here we want to kind of keep epsilon negative and positive here, so we'll scale by negative mu since mu is negative, but it's just to compare these two plots. And once again, you see at very, very low temperatures, so this magnitude of beta mu, very, very large, low temperature, we have a step function, but it's kind of an interesting in this case because we go from 2 to 1 and then 0. And then, of course, as we raise the temperature, this kind of broadens out this step. But you can still, even at here minus beta mu equal to 10, you can still see a little bit of a step feature here in this, this sort of orange curve. Well, that's kind of interesting, and we'll see that there are differences when the chemical potential is positive and negative. Typically, you'll see for, as you could probably guess, if for large positive mu, you tend to get very much, in general, denser systems, denser numbers of particles. And we'll discuss the chemical potential for the ideal gas and for fermions and bosons, and we'll see that. But this is a very simple example. Now, another way to see what's going on here is why you have a step here from 2 to 0. In this case, in this one, you actually go 2 to 1 to 0, is you can look at the exponential terms. That is, if we, in our partition function, let's go back to the partition function here. Where was it? You can see what's going on if you look at these factors here. So at low temperature, this beta would be getting very, very large. And so you can look at these energies. Basically, the energy minus this energy minus the chemical potential, these factors here, and you can see what's going on if you plot that. And that's what I've plotted here, this sort of, for each configuration, I've plotted the energy of that configuration minus mu times the number of particles. And of course, when n equals 0, that's just a constant, right? That's this black line, and it's at 0. And so when mu is positive, what you can see is you raise epsilon from negative to positive. The lowest energy one is the n equals 2, and then at this point, the lowest energy becomes the n equals 0 thing. So at no point is the n equals 1 lower than n equals 2. And so that's why you go from 2 to 0. Because that term, the dominant term below this point, the dominant term in the partition function that gets very, very large compared to all the other terms, is the term with n equals 2. And above this point, the dominant term, the term that as beta goes to infinity, as low temperature, as temperature goes to 0, the dominant term becomes the n equals 0 term. Now, when mu is negative, you can see by plotting these again that you get a slightly different thing, that you start out with the dominant term being the lowest energy term, or the lowest value of this energy minus the energy of the configuration minus mu n being n equals 2, but then you cross to this n equals 1 being lower than 2 and 1, and then you go finally to 0. So that's what's happening there. You can all see that from the partition function. Okay, so that's a relatively simple example. So let's move on now, and we'll talk about a bit more about the grand canonical ensemble, and we'll discuss this for non-interacting particles. So in the previous example, we had non-interacting sites that were distinguishable, and of course we argued that the particles were interacting in a very simple way because we only had 3 configurations to consider. But now we're going to be interested in much larger systems. In fact, we're going to approach both large systems with large numbers of fermions and bosons, and even eventually back to the classical ideal gas, where you have a very, very, very large number of things. So we're going to discuss the situation of large number of non-interacting particles for the rest of this lecture. So if you look back at the last lecture, we already discussed this briefly. We discussed that if we have non-interacting particles, the grand sum can be written, it's also a bit more simple in this case. It can be written as the product of these factors. Because in a non-interacting means the energies are additive, and if we sum over the configurations, we have the sum of all these factors in the exponential, and then we can break that into products. And so in the end, for non-interacting particles, the grand sum is basically the product of these factors for different. So this is the number of particles in state 1 having energy epsilon 1, number of particles in state 2 having energy epsilon 2, and so forth. And so grand sum in non-interacting particles is a bit simpler. It's just a product of these different factors up to if you have R energy levels. And I should say this is for distinguishable particles. We'll come back to that. So grand sum is a product of factors for each single particle state R. So it's quite simple. Now, what we'll see in the next lecture and the coming lectures is that the values taken by this NR depend on where the particles are fermions or bosons. And this is due to, as you have probably encountered in your quantum course, the different statistics obeyed by fermions or bosons. And fermions, you can only put one particle in a given state. Well, actually two if they have different spin. So I guess that's what the game we're playing now with this social distancing. We can't have more than two people meeting up in public spaces. So somehow we're all being fermions at the moment. We'll see how that works. Okay, so yeah, and if bosons, of course, this number is not restricted. But anyway, we'll come back to this. Let's take the logarithm of this, and we see that, well, it's quite simple because when we take the logarithm, this becomes a sum of these logarithmic factors here. And also, it's quite easy to see, as I think we mentioned this in last lecture, that if we wanted to find the mean number of particles in state R, this bracket n sub r, we can find this by taking this derivative. And I don't know at this point why I have this written twice. Oh, yes. I do. It is different. In general, this is, so if we have the partition function, we just take minus 1 over beta times the partial of log z with respect to epsilon r to find the mean value of, or the mean occupancy of n sub r. And of course, if z has this product form, if logarithm sum has this form where you have a bunch of different terms, a sum of terms, then this derivative is only going to select out the term where that term that we called z sub r here, so the particular term within r. And so we find that we only have to take the derivative with respect to the partition function for the state r. So we only get the one term there. Okay. Well, let's consider fluctuations in the grand canonical ensemble. And if you recall, in the last lecture before last, or last lecture, we found that we looked at the case of energy fluctuations in the canonical ensemble. Actually, we looked at energy fluctuations in a canonical ensemble that was made up of n identical subsystems, or particles if you want to consider particles. And what we found was the standard deviation of the fluctuations around the mean of the energy, the sigma mu, divided by the mean u in a system of n identical subsystems, went like 1 over root n, which I said you could think of as a kind of something like the central limit theorem. And it's, as a property of non-interacting particles as well. Well, later, and we'll get to this in detail after we'll have to make a little diversion into quantum statistics and fermions and bosons, but we'll see this. We'll show that this also holds in the grand canonical ensemble. That is this relation for energy, for the fluctuation in energy, and we'll find a similar result for fluctuations in number. That is the mean, the standard deviation of the fluctuation in number divided by the mean in number is 1 over root n as well. So again, the sigma sub n is the standard deviation from the mean particle number, bracket large n. So in other words, let's just look at this. In other words, if we actually look at the probability distribution in the grand canonical ensemble, the probability distribution of the total number of particles in large n, we'd see it look like something here, like this. Here's n on this horizontal axis, and on the vertical axis we have the probability, and this would be the distribution. It would be centered around some n bar, which is just bracket n, bracket large n, and it would have a width, let's say, a full width that's something like delta n. Okay. So what does this tell us then? Well, it tells us that essentially the canonical ensemble, which has a fixed number of particles, and the grand canonical ensemble kind of become equivalent in what you'll hear called the thermodynamic limit, or large n limit, n going to running off to really, really large, so infinity. That is, the canonical and grand canonical ensembles are excellent approximations to each other for large n, right? Now, we'll soon see that this will be very helpful in derivation of quantum distribution functions. And that's because it's easier to use the grand canonical ensemble for quantum distribution functions, and we'll see this, but this is because this is due to constraints on particle numbers, which are kind of difficult, which I have misspelled, difficult to handle mathematically in the canonical ensemble. We'll see this in the next lecture. But let's have a look at this in the present context now. So remember, the general form of this grand sum was, once again, Z is a sum over configurations, and so use that to understand what this sum means. What it means is we're going to sum over n, number of particles, and for each n we sum over the energies of the energy states of n particles, which in general could be complicated if there's interactions and so forth, as we discussed. But we sum over, and we sum over these terms. So every configuration has a term. Every configuration, so every configuration of a particular n and all the levels that are associated with that has a term here. That's what we're saying. So in this so-called thermodynamic limit, that is n getting very, very large, we'll, just for convenience, we'll call n bar this bracket n, so we don't have to write brackets all the time. So n bar, mean n, is sharply peaked with width delta n, as we saw in this plot. So then what we can sort of make an approximation to the grand sum. We'll put n bar here, and we'll have approximately delta n terms that have that, and so we can pull out this factor e to the beta mu n bar, and we'll have about delta n of those terms in this sum. And so we'll see that we have approximately, for the grand partition function, z is approximately equal to delta n e to the beta mu n bar times the sum over, and I missed, this is just a sum over energy. I lost my subscript there. It looks like a sum over energy, of course, these exponential factors. So if we take the logarithm of both sides, then we'll see that log of the grand partition function, z, will be approximately equal to beta mu n bar plus log of the canonical partition function for n bar, that is, plus this log of delta n. And we'll see that this term for a large system is much, much smaller than the other, so we'll just neglect it for large n. And what we'll get then is just solving this for the logarithm of the canonical partition function. We'll see that's approximately equal to log of the grand partition function minus beta mu n. So here we've just taken n to be equal to n bar in all these expressions. So we'll come back to this relation, but we'll see for a large system this is an approximate equality. So then what that means is we can find, in this limit, we can find the mean energy from either log z or log this bold z. So from the logarithm of the canonical partition function or the logarithm of the grand partition function. And so we have this relationship, right? So mean energy of the capital U, which is for the system of n, is this derivative. It's the negative partial derivative with respect to beta of log z, which equals the minus partial derivative with respect to beta of log grand partition z plus mu n. Okay. So with that in mind, let's just get a little preview of the ideal gas. We'll have to wait. We're going to have to take a little diversion. It'll be a really interesting diversion into partition functions for quantum particles before we can actually come back to the ideal gas, the classical ideal gas, which is kind of interesting, and really understand the classical ideal gas from this microscopic point of view. But let's just get a little preview of that with what we've learned so far. Okay, so back in lecture 4, we discussed the canonical ensemble for n non-interacting but identical subsystems. If you go back and have a look at that, we found that for non-interacting subsystems, that the canonical partition function z sub n was equal to z sub 1, which is the partition function for one of these, to the power n. So we looked at this specifically for paramagnetism of localized moments, but we mentioned it's true in general. Well, you might think that you could use this result for a monatomic anonymous. I got to run the spell check. I keep forgetting to run my spell checker on this before I do this. I'll do it next time. For a monatomic ideal gas consisting of n identical particles. So you say, hey, we should be able to use this. I mean, let's forget about quantum mechanics. I mean, we should be able to use this for classical ideal gas, right? Shouldn't we? Yeah. Well, that is, if this little z is a partition function for one molecule in a box with volume V, we think we should have that the partition function for n of those in a box is an ideal gas. They're non-interacting. It should be little z to, the power n, right? That's what you might think. And even if we use quantum mechanics, we could actually find this. We do the problem of a particle of mass m in a box, and we'll show this lecture later in a later lecture. But you can actually evaluate for a quantum mechanical particle in the box. It's all the energy levels. That's this little z is it's proportional to the volume, so it's volume times this factor. And this factor here you can think of by, if you consider the de Broglie wavelength, you can consider this as the inverse quantum volume, by considering the de Broglie wavelength. You probably had a look at this back in the first part of the course when you were working essentially with a microcanonical ensemble. So this VQ is sort of like a quantum volume, right? It's kind of h over the expectation of the momentum to the power 3. So you'd think, well, somehow in the classical limit, even if I have particles in a box and I have these quantum levels, I should be able to use this, right? Well, actually, it will become clear that the equation for non-interacting, if you use this equation for non-interacting particles in a box, this isn't correct, actually. And it's not correct because it describes distinguishable particles. And quantum mechanics tells us that particles are indistinguishable, And so the correct partition function for n identical particles in the classical limit would be, well, this little z to the power n, but divided by n factorial. And this factor of n factorial would, takes care of the the overcounting that would occur if you had distinguishable particles. That is, if I knew I had like a particle 1 that was definitely particle 1, I could label it particle 1, and then I have particle 2 I labeled with label 2, and so forth. That's what I'd get, right? But if they're indistinguishable, it's just that I have a particle in this state, I have two particles in this state, I have 2 particles in this other state, I have n particles in some other state, but I can't say that particle 1 is in that state and particle 2, or particle 3 is in that state and particle 2. Those are not distinct configurations, is what we're saying, and that's why we get in the what we'll see actually in a future lecture is that you get this n factorial to take care of this overcounting for distinguishable particles. Now this is kind of interesting because this factor of n factorial in the ideal gas partition function was a bit controversial in the early days of statistical mechanics. In fact, Schrödinger has a book on this subject, on statistical mechanics, and in there he has a chapter called the n-particle problem. So at that point when he had the book, not even Schrödinger really understood the consequences of quantum mechanics fully. It's kind of interesting. So now, back in the first half of this course, I think you showed that for an ideal gas, and essentially used the microcanonical ensemble, you found the chemical potential for the ideal gas. So you used the microcanonical ensemble that is, you counted the number of states and found the entropy, and you used this relation for the chemical potential, and you got this result, basically. And if I evaluate this, leaving out a small constant that comes out, you see that the chemical potential is approximately, within a small constant, kBt times the logarithm of this quantum volume that we introduced divided by this so-called atomic volume, which is essentially this should be V over N. It's the inverse of the density. I got this. I'll have to correct that. It should be V over N, basically. So the volume per unit particle, that is. Yeah. So, yeah. I got that turned around backwards. I'll fix that. Anyway, so we found that back using essentially microcanonical ensemble and this thermodynamic relation. And so in the classical limit, in fact, what is the classical limit? The classical limit, we'll see, is when basically the quantum volume is much, much less than the atomic volume. That is the sort of just inverse density is what this is. The volume per unit particle. And so in that case, you can see then, just from this logarithm, that the log of a small number here is going to be negative. So for the ideal gas in the classical limit, the chemical potential has to be negative, and really not so close to 0 for large enough t. So as long as t is not too small, this is mu is not. It's always negative in the ideal gas, and it's not so close to 0. Now, if you recall, we looked at the situation for a very large number of particles, and we found that the logarithm of the grand sum could be approximated as the logarithm of the canonical partition function plus beta mu times n, just a couple slides ago. So now, let's take for the canonical partition function the correct result. That is, for capital N particles, we have z to the power n divided by n factorial. So we take account of the fact that particles are indistinguishable. So let's use that, and we plug in this expression for z v over v sub q And we make use of Stirling's approximation, and we expand this. We take log of z. I haven't written in here, but we'll understand what it is. And we'll see then that if we calculate this, I think, yeah. Yeah, this is, we'll use Stirling approximation to expand this guy, and we'll plug in this z just in this form. We just have to use V over VQ here. And if we use the value we found for the chemical potential, that is back here, we see we get a really simple result that the log of the grand canonical sum, the log of the grand sum, we'll see these terms cancel out and it just becomes n, right? So that's a very simple result for the ideal gas. Only if we use, so we have to use the correct result here. And that's really interesting because remember we can get the grand potential, omega sub g is minus kBt times n. It's this is minus kBt times the logarithm of logarithm of the grand sum, if you look back at that. And we also know the equation of state thermodynamically is that this grand sum is minus PV. So again, we'll find the equation of state, PV equals N kBt for the ideal gas, which you should recognize, of course, from either the first part of this course, if not earlier. So in the next lectures, we'll use quantum statistics as a starting point for ensembles, and we'll see eventually we'll get back to the ideal gas, this correct description of the ideal gas, and in the meantime we'll find a lot more, and that's what we'll pick up in the next course. In the next lecture, we will start our discussion of quantum distributions, which we'll derive using the grand canonical ensemble and taking into account the proper quantum statistics. Okay then, I'll see you in the next lecture.